Alright, with this we're going to be looking at a quadratic equation in vertex form. Now, we can look at and say it's a quadratic. We see the x that's going to get squared if we were to FOIL this out. And this is in vertex form. It's nothing for you to memorize quite yet. I want to go through an example and see you get used to it, and then you'll, I think, be quite comfortable with this form. This is, I think, the easiest form to graph a parabola. We know we're going to end up with a parabola. Quadratic is a parabola. It'll open up or down, and this form really makes it quite easy. The first thing to do is look at this equation, and just as when we had point-slope form with a line, think about what would make this equation true. Is there any point that's just plain staring us in the face that will make this equation true? Now, if you look at it, I think it's very easy to see what would make each side equal to 0. If you look at the left-hand side, if y equals 1, that side's going to equal 0. And if you look on the right, if x equals 3, 3 minus 3 is 0. You square it, you get 0. Multiply by 2, you still have 0. So if x equals 3, we get 0 equals 0. So the point 1, no, point 3, x is equal to 3, gets a little tricky sometimes because this is on the right-hand side, but still the x-coordinate. X equals 3 and y equals 1 is a point that makes this equation true. So it's a point on the curve. Now, that doesn't tell us exactly where it is on the curve. It could be anywhere on the curve. What we want to find out next is a little bit more interesting. And this is actually, I think, what really makes vertex form most powerful. I'm going to solve this equation for y by adding 1 to both sides, and the equation becomes 1 plus 2x minus 3 squared. Now, if you look at this second term on the right, something squared is always greater than or equal to 0. You can never square something and get a negative number. So, if we know that this is always greater than or equal to 0, we multiply it by 2, it's still going to be greater than or equal to 0. So this term is always greater than or equal to 0, which means y is equal to 1 plus some number which is greater than or equal to 0. Well, what that means is that y itself has to be greater than or equal to 1, which tells us we can plug in any x we want. The domain is anything, but the range, the function values, are always going to come out greater than or equal to 1. So, well, that's interesting. We know a parabola comes down. This one is going to hit the point 3, 1. That's the lowest point that this function can possibly hit. Y is greater than or equal to 1, so it's going to come down to that 1y value, and it's going to go back up. Not only is this a point on the curve, but it's the vertex of the parabola, the most important point, or certainly I think the defining point on the parabola, where this function comes down and then goes back up. It tells us about the range of the function. So, we have an easy point. We can look at the equation, we can see the most important point, and it just drops out at us. The next thing I want to look at is this 2, because we haven't seen anything about that yet. Now, what about that 2? I want to look at that first by reviewing what 2x squared looks like. And if we do that, a quick table of values. If we plug in 0, we get 0. We're going to take x, we're going to square it and multiply it by 2. If I take 1, I square it, get 1, multiply it by 2, get 2. If we take 2, plug in x equals 2, 2 gets squared, it's 4, gets multiplied by 2, it's 8. So just so far, if we were to make a graph of this, we have that it goes through 0, 0, goes through 1, 2, it goes through 2, 8. 2, 4, 6, 8. Ooh, just makes it. And it's symmetric, it's a parabola, so we can pick up the symmetric point there, another symmetric point here, which means the parabola roughly connects these dots and roughly looks like that. Well, how does that help us with this other parabola, which we now have in the form of y equals 1 plus 2 times the quantity x minus 3 squared? Well, again, a quick little table of values. And let's look at the similarity in how these functions go together. If we plug in 0 here, we got 0. But our vertex, we know, is the point 3, 1. If we plug in 3 for x, 3 minus 3 is 0. We square it, we get 0. Multiplied by 2, we get 0. Add 1, we get 1. Now, if we go 1 unit over to the right, we would go from x equals 3 to x equals 4. What happens there? When we plug in 4, 4 minus 3 is 1. 1 is squared to make 1. That value 1 gets multiplied by 2 to make 2. We add 1 and we get 3. So what happened? We moved over 1 in the x direction and we went up 2, which is exactly what happened over here when we went over 1 and went up 2. So if we're looking at a quick graph of this one, actually I'm going to leave off the axes because that's not anything but a hindrance for us at this point. Let's put the vertex here. We know that vertex is the point 3, 1. When we go over 1, we go up 2. We go over 1 from 3, we get to 4. We go up 2 from 1, we get to 3. This is the point 4, 3. Has the exact same shape as what was going on in this part over here. Now let's see what happens if we go over 2. If we go over 2, in this graph, we went up 2 squared, 4 times 2, which is 8. So do we go up 8? What would happen if we went over 2 and up 8? Over 2 would take us to the point 3 over 2 is the 5 something. And if we go up 8 from 1, we'd get to 9. Is the point 5, 9 going to work? Let's see. If we plug in 5, 5 minus 3 is 2. 5 there. 5 minus 3 is 2. 2 squared is 4. 4 times 2 is 8. That's the 8 we're going up. Add it to 1 from where we started. So we're going up to 9. 5, 9, as expected. So we go over 2, up 2, 4, 6, 8, and that is the point 5, 9. Symmetry kicks in these other symmetric points just as it did before, and we have the exact same shape, just somewhere on a different point in the axis. Instead of 0, 0, it's at 3, 1. So I want to look at just one more and add a little technology to this. Here's a totally different equation. If we look at it quickly, what can we note? We're going to get down, so in about 30 seconds. I'm going to call this the 30-second drill. And it won't be 30 seconds this time, but certainly as we go forward, it will become something you can do in 30 seconds. As you look at this graph, what value of x is going to make the right side equal to 0? Yep, negative 2. Negative 2 plus 2 is 0, squared is 0, times 3 is 0, and we have 0. On the left side, if we make y equal to 1, we're going to have 0 as well. So that is not just any old point. It turns out that is the vertex of this parabola. The other thing you'll be able to note really quickly is the shape. The shape of the parabola is y equals 3x squared. And we'll see that in just a second. So, let's look at this graph. If we are graphing y equals 3x squared, this is at the origin. It goes through 0, 0. Plug in 0, you get 0. Plug in 1, 1, you square it. 1 times 3 is 3. Goes through point 1, 3. If we plug in 2, 2 squared is 4 times 3 is 12. over 2 up 12. Symmetric points kick in on that side, and computer's making a little more accuracy than we're going to have here, but the parabola would connect up these points. So we get a parabola that looks roughly like that. Compensative thickening here and there. Now we write on that. Well, let's see. Well, let's actually do this one. Well, let's see what this one looks like. So we take this function. I'm going to try graphing it, have the computer graph it. Oh, and that's it. It goes through 0, 0. It goes through 1, 3. It goes through 2. 2 squared is 4 times 3 is 12. It goes through 2, 12. And it goes through the symmetric points. And that's the right shape. Now, if we were to graph this one, we already know the vertex is at minus 2, 1. Minus 2, 1 is here. If we then plug in 1 point to the right, it would be negative 1. If we plug in negative 1, excuse me, if we plug in negative 1, negative 1 plus 1 is 1. 1 squared is 2. 1 squared is 1. Times 3 is 3. Plus the 1 is 4. Negative 1, 4. So we go over to negative 1. We go up 1, 2, 3 to the point negative 1, 4. Over 1, up 3. Just as over here, over 1 and up 3. So I'm expecting that to happen. What do I expect in terms of the shape when I go over 2? 2 squared, I expect to have the same shape as this, 3x squared. So you square it multiplied by 3. If you go over 2, 2 squared is 4, multiplied by 3 is 12. I'm going up 12 from 1, takes me to 13. It should be this point up in here. This is going to be the axis of symmetry, where the vertex lives. The symmetric point is going to be there. The symmetric point to 0, 13 is going to be here at negative 4, 13. And I'm expecting a graph that's going to look something like this. A little artistic license might be needed, but that's the idea of the curve. Well, let's see. I'm going to take this and have the computer graph it for me, and there it is. Perfect fit, or near perfect fit. So this is it. When we look at a parabola in this form, we can pick off easily, just as we did with point slope form for a line, we can pick off the x and y coordinates. They're going to make 0 equals 0, and that point turns out to be the vertex. And then we're also going to be able to use the argument of the shape. What does the shape do? Well, you always take whatever the shape is, y equals ax squared. We go over whatever amount, we square that amount, and then we multiply by a. If a, in this case, was 3, we went over 1, squared it, 1, multiplied by 3. Went over 2, squared it, got 4, multiplied by 3, went up 12. That's it. It's going to take a little practice, but it's pretty easy from this form. This is a great form, vertex form.